Okay, hi everyone. Let's go ahead and get started with today's lecture. So welcome to week 2. You've all survived the first week of the class, which is good to see. And so in today's lecture, we'll mostly be covering nonlinear regression. So in last lecture, we saw how we can fit linear models to data for regression problems, and today we'll extend some of those techniques to fitting nonlinear models to data. So just a couple of brief announcements before we get started with the main content of today's lecture. Homework 1, due this week, so Friday at midnight is when that first assignment is due. If you're looking for some help on this assignment, again, your best resources are to try and post questions on that ed discussion board. I see there's been a few questions up there already, which is great, but if you guys have any questions or if there's anything that isn't clear or something you might think is a typo, please go ahead and post that online. Again, we also have 4 TAs for this course. They're all very knowledgeable in machine learning, so do book office hours with them if you're looking to get help with the homeworks or just ask questions about lecture or anything related to the course. So the third problem on the homework is on nonlinear regression, which is what we'll be covering in today's lecture. So by the end of today, you guys should have sort of all the information you need in order to finish up that homework. We'll also be having our discussion sections again this week on Thursday. And the topic of this week's discussion will be on using matplotlib and scikit-learn. So those will be some code tutorials, demonstrations using these packages. You'll use both of these packages pretty heavily throughout the rest of the course. So if you're a little unfamiliar with these, I definitely recommend checking out the discussion sections. And of course, these discussions are really for you guys to get some more exposure to machine learning in general. So if you have questions about, say, lecture or homework, feel free to also bring those to the discussions. I have up here the course schedule for the first 2 weeks, so you can have a peek at what's coming up for the rest of this week. But I'll also point out that I added some resources on partial derivatives. So last time we met, we looked at deriving the gradient for the MSE loss function, and that made pretty heavy use of these partial derivatives. And a couple of you guys asked for more resources on learning more about these, brushing up on them if you're seeing them for the first time. So check out these 2 links. They're up there on the Canvas calendar. Really great way to learn about partial derivatives. So any questions on sort of logistics stuff, course organization before we get started? Great. So in today's lecture, we've got 3 topics. The first is we're going to be covering some more detail on gradient descent. After that, we'll jump into nonlinear regression models. And then we'll very briefly introduce this concept of model selection. And we'll only see model selection for a few minutes, and then on Wednesday's lecture, we'll have a whole lecture dedicated to this topic. So first, just a couple of reminders on linear regression and stuff we saw previously. Our linear regression model is an equation we can write down that takes in some features and tries to predict out a real valued number. So this is for helping us solve regression problems. And let's see. So our linear regression model is some kind of function f that takes in an input feature vector x, and it takes in also some parameters theta corresponding to the weights in our linear regression model, and it just multiplies the weights by the features in order to get out our predicted output. So again, the picture you should kind of have in mind for linear regression models is we're trying to find some line that appropriately captures the trend in our data. This model is, again, learned by minimizing this mean squared error loss function. So a loss function is some kind of function L that takes in the parameters of our model. So it takes in theta 0, theta 1, all the way up through theta d. And it measures how good our model is using those particular parameters. And in the case of linear regression, we're going to use this MSE loss function that compares the true outputs coming from our training data to the outputs from our model. We can actually optimize this MSE loss function, i.e. finding the parameters of our linear regression model that minimize this error, using this algorithm called gradient descent. So here's that update equation for the gradient descent algorithm, where our new parameter vectors after a single iteration are obtained by looking at our previous parameter vectors, theta old, taking a step in the direction of the negative gradient, so kind of rolling our ball downhill, and we take a step of size lambda. And again, physical intuition is really helpful here. we start out our parameters somewhere randomly in parameter space, kind of roll them downhill on our loss surface. So this is some really great physical intuition to keep in mind for this algorithm. So our first topic in today's lecture is just going to be some more details on gradient descent that we didn't see before. So again, on the slide here, this is just the update equation for gradient descent. We've seen it a few times now. But one thing we didn't talk much about is this parameter lambda. This parameter lambda here is called a learning rate, also sometimes called a step size. One of the most important questions that we need to ask ourselves if we're using this gradient descent algorithm is how do we actually choose this learning rate? How do we choose the step size? We call lambda a hyperparameter of our model because it's something that we choose by hand when we're running gradient descent. It's not something that's learned from data. So in practice, if you're, say, fitting linear regression using gradient descent, you'll specify a learning rate before you actually run that gradient descent algorithm. And choosing this lambda value is often one of the most important choices we can make when we're fitting some kind of machine learning model. I'll point out here that we'll see gradient descent over and over again in this course. It's not limited to just fitting linear models. So we'll use gradient descent to fit things like neural networks or logistic classifiers that we'll see in a few weeks. And so it's really good to really make sure you guys understand the details of this algorithm. So here in these three plots, I'm plotting sort of a loss surface in one dimension. So this parabola-shaped curve is some kind of loss function. On the x-axis is some representation of maybe the parameters of our model. And if we choose this learning rate lambda to be too small, what we'll see is that it requires very many iterations of gradient descent to actually converge down to the minimizer of this loss function. So if we make lambda too small, our algorithm is going to be very, very slow. If we choose lambda just right, it'll take an appropriate number of steps to get to the minimizer of this loss function. But if we choose lambda to be too large, what can happen is we can actually overshoot the minimum. So maybe we start our parameters out here at this yellow dot, but if our step size is too large, we just take too big of a step, we can step over the minimum, kind of the bottom of this bowl-shaped function. And if you make lambda really large, what can actually happen is your iterates can diverge. So rather than converging to this minimizer, your loss can actually kind of blow up to infinity. Now, obviously, that's not what we want to happen when we're trying to fit a model. We don't want our loss to get worse over time. And so it's important to kind of balance between making lambda too small, slow convergence, and too large, which can lead to no convergence at all. So how do we actually pick a value for lambda? Well, kind of the most straightforward, easy thing for us to do is just try out a bunch of different values for lambda and see what happens. So in a little more detail, what I mean by that is you can fix a value for lambda, run gradient descent and fit a model, and then evaluate those models that you get out from doing this and just pick whichever one works best. This is really the most straightforward option. It's probably what you would guess to do if you had never seen something like gradient descent before. But one of the cons of doing it this way is that it can be very costly to do this. Oftentimes, we want to try out a lot of different values of lambda. Maybe there's 100 different values of lambda that you'd like to try. This then involves fitting 100 different models. And if every model takes just 10 minutes to fit, which is relatively short for a machine learning model, it'd be really expensive to try out a whole bunch of different parameters here. Later on in the course, when we see models that are more complicated than linear regression, we'll see other hyperparameters of the model. So we'll want to tune the learning rate plus a bunch of other things about our models. So trying to do them all sort of simultaneously in this kind of naive way of just trying them out is just going to be very, very expensive. But it might work for linear regression where we just are tuning the learning rate. So it's an okay option if you've got nothing else. So to actually help us kind of diagnose a learning rate to see if it's too large or too small, one thing we can do is plot what are called learning curves. So these learning curves have on the horizontal axis here the iteration count, so how many steps of gradient descent have I run. And on the vertical axis, I'm actually plotting the loss function. So this is the MSE corresponding to the values of theta at a particular iteration on the x-axis. If you have a very high learning rate, maybe this yellow curve we see here, what can happen, as I showed you before with that 1D example, is your loss can actually diverge. So your model isn't getting better over time, it's getting worse over time. This is just because we're overstepping that minimum. We're kind of blowing up off to infinity. If your learning rate is too low, shown in this blue curve, your model is going to take a very long time to converge. And in fact, it might converge to something that just isn't a very good fit. If our learning rate is too high, but not extremely high, you might see something like this green curve, where the loss decreases but flattens out at a sort of suboptimal value. This is because we're kind of bouncing around the minimizer. We're not actually being able to kind of land in the bottom of that bowl-shaped function, just because we're taking steps that are far too large. And our optimal learning rate, of course, is something that decreases fast and decreases to a low value of the loss. So plotting these learning curves can be a nice way of kind of visualizing and diagnosing, checking if your learning rate is too large, too small, etc. Another strategy you can use for choosing this learning rate, it's a little bit more advanced, is to actually use an adaptive step size. What I mean by an adaptive step size is that our learning rates now depend on the iteration count t. So if I take t steps of gradient descent, I'm going to let my learning rate depend on that sort of step count. And the idea here, sort of the intuition of why this makes sense, is you might want to start your learning rate out high in order to get close to the minimizer of your function. So again, in gradient descent, when we start our algorithm, we just randomly initialize this theta value. And there's no guarantee that it's anywhere close to a minimizer. So at the start of gradient descent, we kind of want to take large steps. We want to move close to that minimizer pretty quickly. But then as we get closer to that minimizer of our loss function, we might want to decrease the learning rate to sort of fine-tune, i.e. to get closer and closer to the minimum of that bowl-shaped function without overstepping that minimum. So one way to actually do this is with something like an exponential decay learning rate, where lambda t, again the step size at iteration t, has the following form, where lambda naught is some initial learning rate. So we can fix this to just be some number, maybe like 10 to the minus 2, 10 to the minus 3. And then we also fix some kind of decay rate, which is just some positive number k. And so what we're doing here is we're taking some initial learning rate and just decreasing it exponentially over time. And this will have this effect of starting out large and slowly decreasing our learning rate. Another strategy that you might use to decay your learning rates is a linear decay schedule. So this equation might look a little scary, but I'll show you a picture on the next slide that hopefully will convince you it's not too bad. But it's a similar idea, where we start out with some initial learning rate, lambda naught. We specify also some minimal learning rate, lambda min. And then we linearly interpolate between lambda naught and lambda min. So the equation in the sort of first part here is just a linear interpolation. And to do linear decay in this way, we'll also need to choose a number of decrease steps, capital T. So we decrease our learning rate for a total of capital T steps, and then we fixed it at lambda min for the remaining sort of update steps. So here's some graphs showing you what these two learning rate schedules might look like. On the left is that linear learning rate. So again, we start at lambda naught, some initial value of the learning rate, decrease it linearly over time until we hit t iterations, and after t iterations, we just fix it at lambda min. The reason we don't want to go to a learning rate of 0 is because, well, if our learning rate gets too small, again, you saw it's not going to take us closer and closer to the minimum. We might get kind of stuck. So it's a good idea to kind of cap it out at some minimum value. And then on the right-hand side, I have a graph of the learning rate versus the number of iterations for that exponential decay. And as you might expect, it looks like an exponential graph. You might notice here that I now have introduced even more hyperparameters into my model. So I need to choose, for the linear decay rate, I need to choose like an initial lambda naught, I need to choose a lambda min, I need to choose a capital T. And in practice, choosing these numbers requires a ton of experimentation. So oftentimes you might train a order of 100, maybe a couple thousand different models using different learning rates and various parameters here before you really find what model fits your data best. Okay, so beyond the learning rate, there's also a couple other things about gradient descent that you guys should be aware of. The first is that for a linear regression problem, using the mean squared error loss function, as we've been doing, our loss, L of theta, is actually what's called a convex function. So most of the sort of loss surfaces I've showed you so far have indeed been convex. And this really means they're just kind of like a quadratic shape, a sort of bowl-shaped function. But having a convex loss function is a very nice property. In particular, convex loss functions have single, unique global minimizers. So there's really only one point in this function that minimizes the loss surface, kind of down here at the bottom. And in fact, if you run gradient descent on a convex loss function, with an appropriate choice of the learning rate, plus some additional assumptions I won't go into here, you're actually guaranteed to converge to the minimizer of this function. So this is really nice. We have some theoretical guarantees that tell us gradient descent actually really works. One thing to note, though, is that how you initialize your parameters can have an effect on how well gradient descent actually performs. So again, thinking of some physical intuition, if I start my ball sort of up here where the loss function is really high, it's going to take a lot of steps before I kind of slide down this surface and converge to the minimizer. In contrast, if I start my ball pretty close to the minimizer, it's going to take fewer steps. So gradient descent can actually be pretty sensitive to how you initialize these parameters. In practice, you often can't do much better than just kind of randomly picking your initial parameters, but it's something to be aware of that this initialization does matter. If you guys are interested in sort of this convex analysis type stuff, I'll point out a really great book here by Boyd and Vanderbeek. This is kind of the Bible on convex optimization. So if you want to see a proof that gradient descent actually converges, if you guys are into the math aspects, then definitely check this book out, but by no means is a requirement. Later on in the course, we'll see plenty of examples of models which correspond to non-convex loss functions. And in this case, if you run the gradient descent algorithm on a non-convex loss function, it might only converge to a local minimum. So this function we see here on the right-hand side is an example of a non-convex function, and it no longer has just a single unique minimizer, say this point here, but there's also some points here that correspond to a local minimum. And what can happen is gradient descent can actually get stuck in these local minimum, and in general, you have no guarantee that if you run gradient descent on a non-convex loss function, that it'll actually converge to the global minimizer. And again, which minimum it converges to is very sensitive to the initialization of the parameters. Okay, so for another illustration, if we start our parameters, say here, and run gradient descent, it might converge to this local minimum, which doesn't look very good. Same thing here, it'll kind of roll downhill, converge to this local minimum. But if we get lucky and just randomly initialize our parameters in a spot that is close to some global minimum, it's possible that gradient descent actually will converge to that global minimizer. In general, our loss surfaces, our loss functions, can be very complicated. For example, neural networks, which we'll see in a few weeks, are known to have these extremely, extremely complex loss surfaces. And in fact, understanding the geometry of these loss surfaces is an open and very interesting question in machine learning. So if you like geometry, maybe you guys can read up a little bit on neural network loss surfaces. In practice, a neural network often has something like millions, if not billions, or even trillions of parameters. And so these figures I'm showing here for the loss surfaces are actually just a really low dimensional projection of those very, very high dimensional loss surfaces. So here, even in 2, 3 dimensions, you can see these loss surfaces are very nasty, not fun to work with. But trying to imagine this now happening in millions or billions of dimensions should give you a sense of why optimizing very complicated models can be quite difficult. Another aspect of gradient descent that you guys should be aware of is feature scaling. So for any gradient-based learning method, say gradient descent or some other kind of algorithm, it's useful if all of your features live on kind of the same scale. And what I mean by that is that you don't have any particular features that are much larger or much smaller than other features. So you might have, say, a medical data set where one of your features corresponds to a patient's age, and another feature corresponds to a patient's, say, weight. Ages are somewhere between 0 and 100, but weights, kind of live on a different scale than that. And so oftentimes what we'll do is we'll actually just rescale our features so that they all kind of have the same ranges. A kind of standard way of doing this is called standard scaling. And in order to do standard scaling, what we do is we will actually subtract the mean from each feature. This will kind of center every feature, so it has a mean of 0. And then we'll divide by the standard deviation of that particular feature. Okay, so here's an equation. X sub ij is, again, the value for feature x. So for data point I and feature j, what we do is we take that particular value, x sub ij, and subtract off the mean of feature j. So again, in our medical data type example, this might be the average, say, age of a patient. And then from every patient's age, we'll subtract that average age. And again, this has the result of centering these features so that they have 0 mean. And then what we do is we divide by the standard deviation of that particular feature. So again, this will be like the standard deviation of the ages in our data set. And what this does is it makes it so that every feature now has mean 0 and standard deviation 1. And this lets us have all of our features just, again, have the same kind of scale. The reason this is useful for gradient-based methods is that if one feature lives on a much larger scale than the other features, what can happen is it'll have an oversized impact on the gradient. So, for example, if one feature is very, very large, it's going to affect the updates much more than the other features will. So to actually achieve this standard scaling, thankfully scikit-learn comes with a nice kind of one-liner that will do this for you. And so, yeah, you can check out the documentation for this code snippet here. In practice, you pretty much always scale your data before sticking it into a machine learning model. There's really no reason not to scale your data. It generally doesn't hurt. So kind of good practice to do this before fitting a model. So for some more intuition of why scaling helps for gradient-based methods, we can again think back to this sort of geometric picture looking at loss surfaces. So here I'm plotting the contours of the MSE loss function. So again, we're just doing linear regression on some data set. Horizontal axis corresponds to the first parameter in my model, and the vertical axis corresponds to the second parameter in my model. If all of my features are scaled using that standard scaling method, and you run gradient descent, what you can see is, gradient descent pretty quickly converges to this minimizer. And all of these contours are kind of, they kind of have the same shape. They're almost circular. It's a very symmetric loss function. In contrast, if we don't scale our features, maybe feature 1 has standard deviation 5, so it's on a much larger scale than the other feature. What happens is that our loss surface, even though it's still convex, it still has a unique minimizer, it's no longer kind of symmetric, and in fact is very sharp. So here, what happens for gradient descent is we kind of bounce around this minimizer due to just the geometry of this loss surface. And so in practice, scaling can often lead to quicker convergence of gradient descent, or in fact convergence even to a better model. Okay, so in gradient descent, we also need to specify a way of stopping. So how do we know how many iterations we need to run before we cancel our algorithm? And there's various ways that you can actually determine when to stop gradient descent. The first method is often the simplest and most often used in practice, is if the magnitude of your gradient vector goes to 0. So for example, you might take the sum of all the values in your gradient vector, and if it's smaller than some small fixed threshold that you specify, then you can finish your gradient descent algorithm and return whatever parameters you found. Second method you might try out is if your loss stops changing. So you can measure the MSE over time, kind of in those sort of loss curves that I showed earlier. And if the change in loss is very small, then this is another way of detecting convergence. A third method that I don't necessarily recommend, but something you could try, is looking at the actual parameters of your model. So if, say, the weights in your linear regression model don't change very much over the last 2 iterations, then again, this could be another method for detecting convergence. And again, methods 1 and 2 are really typically what gets used, but method 3 is an alternative if you'd like to try something else out. There's another method that we'll discuss a little bit later, which is that you can monitor the loss on what's called a validation set. So keep that word in mind, validation set. We'll see it in a little bit. Okay, and then for our last slide on gradient descent, I'll point out that gradient descent isn't the only algorithm that we could use to fit models. There's a lot of actually different variations on this basic idea of doing optimization in parameter space. And in fact, there's a whole community in machine learning of people who just work on optimization algorithms. They don't work on models, just new algorithms for actually fitting models. A kind of general class of these more advanced optimization methods are called momentum methods. So if you've ever heard of something like ATOM or gradient descent with momentum, those are examples of momentum-based optimizers. And again, some physical intuition here really helps. Rather than just rolling our ball downhill, we'll also keep track of sort of the momentum of this ball. And what this can do is it can help us avoid that overstepping problem, where we kind of shoot over a minimum because we're taking too large steps. Often this can kind of also smooth out gradient steps. So we saw that example of the very sharp loss function where our gradient descent iterates bounced around. And those momentum methods can really help solve those types of problems as well. Another class of optimizers that you might run across are second-order methods. So gradient-based methods compute the first derivative of our loss function via that gradient. But you could also compute the second derivative of our loss function. Kind of gives us curvature information about the loss surface. And occasionally these get used to also fit models. One problem with these second-order methods is that they actually scale pretty poorly. So oftentimes they scale cubically in the number of features that we have. And so in machine learning, if we have something like 100 features, maybe 1,000 features, these methods are just going to be too slow. So gradient descent is a nice trade-off between speed and also kind of flexibility of the optimizer. Okay, any questions on the more details of gradient descent that we've gone over? Yeah. Yeah, so the idea is, okay, imagine we start with this loss function on the left. It's kind of like a quadratic, symmetric bowl-shaped thing. And we took one of these axes and we stretched it out. That would be like scaling one of our features by like 10. We make it a much larger order of magnitude. Rather than having that kind of quadratic bowl-shaped thing, you now get a very thin, sharp-looking surface. And that's exactly what you see in the second plot here. So you're really kind of changing the geometry of these loss surfaces via scaling. And it can help with gradient descent. I think the red arrows point out exactly why that is. Yeah, another question in the middle. Yeah, this is a really good question. Just to reiterate, the question is what happens if we start out in like a flat part of the loss function. And what will happen is gradient descent is going to get stuck. So in flat regions, the gradient is 0. And so gradient descent says, okay, I'm not going to make any steps. I have 0 gradient. And so that's another problem you can run into with gradient descent is it doesn't find a minimizer. It just gets stuck. But this is oftentimes not something we worry about. Yeah. It'll also get stuck. So once you're in a sort of flat region, you're stuck there forever. Yeah.
Another question about the scale. Does that mean it's always better to normalize all these parameters?
Yeah, oftentimes it doesn't hurt to normalize your data like this. You might not see huge gains in performance, but it can't hurt to do it. So most of the time, yeah, scaling your data is a good first step. Yeah. Do you mean like numerical issues or? you can run into numerical issues, but hopefully your data isn't on such a scale that that happens. To run into a numerical issue here, dividing by a very large standard deviation, you'd have to have some pretty big numbers in your data set, and you don't really often run into that issue. Okay, I think in the interest of time, we're going to move on to the next part of today's lecture, which is on nonlinear regression. And the question that I'd like to pose to you guys is, how can we do regression if our data set isn't at least approximately linear? So here, we went out and collected some data. This is a 1D regression problem. This is clearly not a linear data set. If we fit a linear regression model to this data set, here, this is that black line. It's the best possible linear regression model, has the smallest MSE. We can see this doesn't fit our data at all. So maybe let me take a hand from the audience. Any ideas on what I should do? How should I fix this? Yeah.
The function will be a straight line in a quadratic space, so you can quadratic space.
Yeah, exactly. So the suggestion was, okay, this looks like a parabola, so maybe we can try and fit a parabola to this instead of a line. That's exactly what we're going to do. So let's say, for our example, that our data only has one feature, x1. A linear regression model, shown here, this equation, can unsurprisingly only fit linear relationships. In contrast to linear regression, we could do what's called quadratic regression, where we're no longer trying to find a line of best fit, but rather a sort of parabola of best fit. And the equation for our model for quadratic regression has the following form. It's very similar to linear regression, so we've got a bias term, theta naught. We've got a term theta 1 corresponding to kind of the linear effect of x1. We've got a new parameter, theta 2, which is multiplied by x1 squared. So again, we're trying to find these values, theta 0, theta 1, and theta 2, to create a parabola that matches our data as kind of best we can. In sort of another level of generality, we can consider polynomial regression. So rather than just looking at x1 squared, we can go all the way up to x1 to the pth power, for example. So if p is 3, you're doing like cubic regression. If p is 4, you're doing quartic regression, so on and so forth. And here p is what's called the degree of the polynomial expansion. Ignore the second degree. Okay, so let's look at some examples of what polynomial regression looks like on this data set that I had showed you guys before. So again, p equals 1 is our linear regression model that we've already seen. Doesn't fit our data very well. If we fit a parabola to our data, we're doing quadratic regression, and visually this looks pretty good, right? If we go up to a 5th degree polynomial, it looks even better. If we go up to a 15 degree polynomial, well, just by staring at this, you can see that it fits our data really well, right? It goes through pretty much all of these blue points exactly. But this might not be what we actually want to happen in polynomial regression. So we'll see some more information about this sort of p equals 15 case in a little bit. But, again, this is just to demonstrate that we can choose the degree of our polynomial and get better and better fits to some nonlinear data. Okay, so let's see some more details, put some equations down, and talk about how to actually fit a polynomial to our data. The first step is we're going to fix a degree for our polynomial regression model, p. Again, this is a hyperparameter of our model. We're not learning p from data. We're going to fix p before we do any model fitting. Now say we have some feature vector x, which has d features. And what I'm going to talk about now is what's called a polynomial feature expansion. So lots of symbols here, but it's, I think, fairly intuitive concept. So let's say we're doing a degree 2 polynomial feature expansion. What I'm doing is creating a new variable z, which is the output of this function, phi sub 2 of x. So phi sub 2 is the 2nd degree polynomial feature expansion of x. And what it is, it's a new feature vector where the first feature is 1. So this is that bias term thing I had introduced in a previous lecture. We then have our d features, just directly copied from x. Then we square all of our features. So we look at x1 squared, x2 squared, so on and so forth. And then we also need to look at these sort of interaction terms between our features. So we can look at x1 times x2, x1 times x3, so on and so forth, and then also x2, x3, et cetera, et cetera. Again, this function, phi sub 2 of x, is what's called a feature map. Really what we're doing is we're taking in some feature vector x, doing some transformation on it, and spitting out or returning a new feature vector z. And again, really the key idea here is we're creating a new feature vector based on our old feature vectors that in this case consists of all the first order and all the second order kind of combinations of our features. And if we put a coefficient, a theta, in front of every one of these features, then we're doing polynomial regression. In general, I showed you guys in the previous slide the equation for a degree 2 feature expansion, but the polynomial feature expansion in an arbitrary degree p, it's the exact same idea, except we don't just go up to second order terms. We also look at, say, x1 to the p, xd to the p, x2, x3 to the p minus 1. So it's all of our feature combinations that have degree less than or equal to p. Okay, let's look at a concrete example here. Let's say our feature vector has just 3 features in it. So we've got our bias term, 1, and we've got x1, x2, and x3. So maybe this is like a patient's age, their height, and their weight, for example. To compute our degree 2 polynomial expansion of this feature, what we do is we first copy over x. So we've got 1, x1, x2, and x3. We look at the squares of all of those features. And then we look at all of the interaction terms between those features, having total degree at most 2. So we look at x1 times x2. Again, this has degree 2 because it's a product of 2 variables. x1 times x3, same thing. And also x2 times x3. And this is all of the possible feature combinations having degree at most 2 here. Okay, so homework problem, if you feel like thinking about this a little bit more. To check your understanding, you can also compute the degree 3 feature expansion for this vector. It's the same idea, but now we'll consider all of the sort of third order terms. Okay, so now we've seen how to do these feature expansions. Again, it's some transformation of our data. After doing so, how do we actually fit a polynomial to our data? And again, let's just consider our data having a single feature x1. Our degree p polynomial regression model that I had shown before has the following form. It's again just thetas times our inputs, but we're also considering x1 squared and x1 to the p as inputs to our model. Doing a polynomial regression actually is equivalent to doing first a degree p feature expansion, followed by a linear regression on top of that. So what I mean by that is we can first take our feature vector x, apply this feature map, phi sub p, creating new features, z. These are just sort of all the polynomials of our feature. And we get out some new features, which I'll call z0, z1, all the way up to zp. And if I write down the equation for a linear regression model on top of these new features, z, it has the following form. Theta 0 plus theta 1 z1 plus blah, 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 plus theta p times zp. Now this is exactly the equation for a linear regression model, except on our new feature z. And we can also write it in this convenient sum form. And so the point I'd like to emphasize here is that polynomial regression is really not that much more difficult than doing linear regression. We just have this additional step of computing these what are called feature expansions of our data. We can, of course, do the same thing if we have more than one feature in our data set. We'll just have to consider sort of more complicated feature expansions, but same intuition works. And really, again, the key idea is polynomial regression is just linear regression with some new features that we create. So, to give you guys more of kind of like a pseudocode look of how you actually achieve this in practice. Again, you fix the degree of your polynomial p. You compute these feature expansions, z sub I, for every data point, x sub I in your data set. So you compute these polynomials. You can do this in a one-liner using scikit-learn. So there's some code out there that'll achieve this for you. And then you just fit a linear regression model on top of those new features z, say using gradient descent like we had done previously. And again, in scikit-learn, we've got linear regression models already implemented. Fairly straightforward to use these things. Okay, so any questions on polynomial regression? Yeah. Could you ask that again? Yeah, if you'd like to try and implement, this polynomial feature expansion thing by hand, it can be a little hairy. But for all intents and purposes, at least in the homework, you'll just be using the scikit-learn implementation of this. Yeah. So the purpose is that if we go back to our example that we saw, the only regression model that we know so far is linear regression, right? We only know how to fit linear models. But linear models kind of aren't enough, right? If we fit a linear model on this data set, it's not a very good fit to our data. So we need, some kind of more powerful tool than linear regression, and polynomial regression is a nice way of doing that. Cool, any other questions? Yeah. Yeah, good question. I'll get to it in 2 minutes. Yeah, another question? Yeah, I believe so. The question is, the size of our new feature vector coming from polynomial expansions is exponential in the degree of our polynomial. And yeah, so it does make it computationally more expensive to do this. But there's tricks to get around this. Like you might only look at a few of the polynomials instead of all of the possible combinations. It's a great question for next lecture. Okay, cool. In the interest of time, let's move on. So, got another question for all of you guys. What would you do if your data looked like this? Any thoughts? Yeah. Yeah, so it said cosine. So rather than doing a polynomial feature expansion, we could do something like a trigonometric feature expansion. So, rather than taking our data and fitting all of the polynomials that we can to it, we can do like a trigonometric expansion where we take x1 and we compute sine of x1, cosine of x1, sine and cosine at a higher frequency, so on and so forth. So this idea of feature expansions is really quite general. And if you think about your problem and have some domain expertise, you might be able to actually kind of craft these feature maps that help you model your data. Okay, I'd like to give you an example just showing you that this isn't a totally made-up thing that we're just doing for the purposes of the course. There actually are data sets out there that look like this. So this is a real data set. It's a time series data set, where on the x-axis we have time, so essentially what time of the day it is, what time of week it is. And on the y-axis we have the number of bike rentals in some city. You can see this definitely has a periodic trend to it. And if we like to do regression on this kind of data, something like a trig feature expansion might be quite useful. This practice of designing feature maps is often called feature engineering. And so a lot of machine learning work often goes into designing these maps and building features that are appropriate for your data. Okay, and so for the last topic in today's lecture, with about 5 minutes we've got left, we can very briefly introduce model selection. So someone asked earlier, what degree of polynomial should we use? How do we actually select this degree? And of course the idea is, well, we want to choose the polynomial that fits our data best, but doesn't fit it so well that it doesn't generalize to data we didn't see during training. So here, probably p equals 5 is the best of the options I'm showing here. And the key idea here is that the complexity of our model, in some appropriate sense of complexity, should somehow match the complexity of our data. If our model is too simple to really appropriately capture the data that we have, we're in a scenario called underfitting. Our model is just not good enough to actually capture our data. So we see an example of underfitting with this linear regression model on this kind of quadratic-looking data set. On the flip side, we might have overfitting. This is where your model is too complex. It fits the data so well that it can't generalize to new data that you didn't see during training time. And so our 15-degree polynomial is showing an example of an overfitting scenario. And this trade-off between overfitting and underfitting really introduces a lot of tension into machine learning. You need to somehow find the model that's just right for your data, such that it's not too simple and not too complex. Okay, and I'll give you guys kind of a basic idea of what you can do to actually select the polynomial degree, which you can think of as kind of selecting the complexity of our model. So we're looking at the same data set. In the blue dots, I've plotted the training data for my model, i.e. this is data that my model is actually fit on. And let's say, after I fit my model, I went out and deployed my model in the real world, making some kind of predictions. This is often called like validation data. These are the red dots I have plotted here. And one thing I'll point out is we've got some red dots in this region, but no blue dots. So our model, during training, has no idea what to put in this region here, but during validation, the red dots follow, kind of the curve you could imagine should be there. If I compute the mean squared error of this linear model on the blue dots, the training data, I get something like 0.22. And if I compute the mean squared error on my red dots, the validation data, I get an MSE of something like 0.23. So these are roughly the same. What this indicates is that our model does about as well on the training data that it did see and the validation data that it didn't see during training. If we use a degree 2 polynomial, we see that the training MSE and the validation MSE both go down. So our model is doing better, it has a lower value for the loss. If we bump it up to a 5-degree polynomial, our MSEs both go down again. This is our best model so far. It's got the lowest loss on both the training set and this validation set. But interestingly, if we now go to the degree 15 polynomial, the training MSE in blue still goes down. It's an even better fit to our training data. But now, the validation MSE actually went up. So rather than decreasing for the red points, our model is doing worse for data it hadn't seen before. And this is really kind of the key indicator that your model is overfitting. It does really well on the training data, it does well on the data it's seen, but it's so complex that it's not generalizing to new data that it hadn't seen during training. And so one simple method for detecting overfitting versus underfitting in your data sets is to go out, collect a whole bunch of training data, and then partition your training data into different subsets. Our first subset we'll call a training subset, and this is the data that's actually used to fit our model. So these are the blue dots in that example we saw. The second subset we'll create is called a validation subset. This is data that's held out from the model. So the model isn't trained on this data. We're just keeping it, setting it aside. And what we're going to do with this validation is we're going to evaluate the model we fit on the training subset on this held out validation data. In some sense, it's like we're simulating as if we had gone out and collected more data to test our model on. And what we can do with this validation subset is use it to detect overfitting and underfitting, and we can use it for things like model selection, picking the degree of our polynomial, as well as things like tuning hyperparameters. At the end of the day, what we're really interested in a machine learning model is not fitting the training data well. We already have that data. What we're really interested in is generalizing that model and applying it to new data we hadn't seen before and making predictions with that data. So this training validation split is a nice way of kind of simulating what we really care about. Oftentimes, we have a third set, a testing subset, that we only look at the very end of our machine learning pipeline. We'll say more about this next lecture.